Today we are going to talk about a very important idea called the mean value theorem or Lagrange mean value theorem, named after its originator, the famous mathematician Joseph Louis Lagrange. Mean value actually means average value. I understand most of us know what is the meaning of average. It simply says that averaging actually is a proper policy, it works. Now, what does it say? What does the Lagrange mean value theorem says? It says let f from AB to R be a function be a given function. Suppose that number 1, f is continuous on AB. CONT means continuous, these are just short forms I am using just to improve the economy of writing. And number 2, f is differentiable on the open interval AB. So, I am suggesting it has to be on the open interval AB, right, the differentiability. If these two conditions are satisfied, then there exists, so this is the symbol of there exists, x element of AB, actually in the open interval AB, of course, I will just x such that f dash of x is equal to FB minus FA by B minus A. Now, this is the statement of the Lagrange mean value theorem. So, I will first show how to interpret this idea, what it means. So, it has one mathematical interpretation and it also has a physical interpretation. So, let us first look at the mathematical interpretation of what does it mean. So, if I have a function, I am trying to draw the graph of that function, say A to B. So, maybe this is a continuous and nice functions here. Okay. Now, what it says, so if you look at this point of the graph, then this is nothing but AFA. And if you look at this point on the graph of the function, so this is your x and this is your y, so this function is nothing but y equal to fx. So, this function is actually y, the graph of the function y equal to fx. So, at this point it is b f b. Okay. So, what is important is the following. Now, what does this thing mean? Now, if you join these AFA and BFB by a straight line, so call this straight line say L, call this straight line L, then slope of L is nothing but FB minus FA by B minus A. Derivative has a very interesting explanation in the sense that, which I think we have not told you in your class, in your lectures on derivative, a derivative has a very interesting interpretation. So, the derivative is nothing but the slope of the tangent line at a point x f x. So, here if you are having a function is differentiable say, and this is the point x f x, and this is a tangent. So, we have also mentioned it, but this slope, so if this is theta, then tan of theta is the derivative at x f x. So, that is I would ask you to go back and think why a derivative at a point x f x would actually be so. Because what does the definition of the derivative says? It says that if you take some point here which is say this is x, then this is x plus h, then you will have some point whose coordinates are, this coordinates would be x plus h and f of x plus h. So, basically you take 2 points and you basically look at the secant joining it, the chord. So, you do it, and as you make h smaller, the chord finally comes and aligns with the tangent, and hence in the limiting case the tangent, the slope of the tangent at the point x f x becomes the derivative. So, here what it says that slope of the line L is such. So, now I can always find an x in the interval a b such that the tangent drawn at the point x f x to the graph of f x is exactly parallel to the line L, because what it says that there exists an x such that this is equal to f x, f dash x, where x is some element in a b. So, which means that the slope of the tangent to the graph at the point x must be same as L. So, these are two different lines, but they have the same slope, and hence it must be parallel. So, basically there must be a tangent to the graph of the function f which is parallel to the line L. That is the meaning of the statement. Now, let us give a physical explanation of what we have just written down as the Lagrange mean value theorem. The physical explanation is the following. So, suppose a car starts from time x equal to 0 and ends at time x equal to t. In that the car has moved a certain distance. So, in this axis is the time axis and this is the distance axis. Okay, there is a time axis and then there is a distance axis. Now, so at the point x equal to 0, the distance travel is 0, 0, 0, and at the point x equal to t, the distance travelled is say, so the distance is a function of time, let us call it f of x, so the distance is f of t. So, this is nothing but t f of t. So, now how do I calculate the average speed in over this distance? So, the average speed is nothing but, so if I want to calculate the average speed, so the average speed is nothing but the distance travelled in this time interval divided by the time taken. And now, assuming that the path of the car which has been described is a nice function with differentiability and continuity properties just as it. So, what does it say? That there would be a point, so here is your line joining So, what it says that there exists a point by the mean value theorem such that the tangent to that point on the graph, say this is some x. So, the tangent at that point of the graph is parallel to this line joining 0 0 and TFT, which means that during the travel there must be a time point when the car travels at the average speed. There must be an instant where the velocity exactly equals the average speed of the car. This is quite an natural thing to happen. So, that is exactly the physical meaning. It is a very kinematical problem, it is the physical meaning of the derivative, right. So, we have some ideas. Now, what does this mean value theorem does? We are yet to prove the mean value theorem and we will do the proof at the end, but let us first see what sort of help the mean value theorem can do to us in our studies. So, when do you apply the mean value theorem? What is the situation when you apply the mean value theorem? Suppose you want some information about f, some information or info in your language, info about f, and we have already got some info about f dash, then use the Lagrange MVT or just then use the mean value theorem. I will give you an immediate example which you will be quite surprised to see. Many of you might not have thought about it. If the function f be such that f of x is equal to a constant c, then it is very simple for you to prove without much difficulty that f dash of x at any point x is just 0. It is just 0. But if I ask you the reverse question, that if f dash of x is equal to 0, if f dash of x is equal to 0, is f constant? So, I am asking now the reverse question. If f dash of x is equal to 0 for all x, say in an open interval, or say all x element of AB or whatever, or what the whole R, does not matter, then is f constant over AB. So, that is the sort of questions we are going to ask. Now, here as I told you, the mantra is this, that if you want some info about f and you already have some info about f dash, then use the MVT, then use the mean value theorem. That is the key idea of when you want to use the mean value theorem. So, how do we do it? So, take the interval AB on which the derivative is 0, and take any points, say x and y in AB, any 2 points, any arbitrary point, does not matter which point. Then by the mean value theorem, fy minus fx divided by y minus x is equal to f dash z, where z is an element in the open interval, sorry, xy. So, now, but in this whole interval, so z is somewhere here. Now, in this whole interval a to b, the functional values of f dash is 0. So, f dash z is also 0. So, this would imply that Fy is equal to Fx. For all xy in AB, because this has been chosen arbitrarily, so it does not matter. So, whatever any two points you take, they would have the same value. So, if you take any other point z, it will have the same value as Fx and hence the same value as Fy, which means F is constant. So, this is a application of the mean value theorem, right. Because this is a very important and interesting application. For example, if you have another simple application of what we have just. So, once we know this, I will show you another simple application of this. The simple application is the following. So, if f dash x is equal to g dash x, then it implies that Fx minus gx must be equal to 0, equal to constant. This is an obvious application of this idea, because that is, if f and g have the derivative same, then they can only differ by a constant. The algebraic non-constant parts must be equal. So, this what does it mean? F dash x is equal to g dash x. This implies so that f minus g dash of x is 0, and from the above result, this is true for all x, of course. So, if from here there the result above that we have shown that if f dash x is equal to 0 for all x, then f must be constant. So, f minus g of x is constant, and by definition this is nothing but Fx minus gx, and that is constant. Calculus is about change, and derivative is the most important tool which encompasses that idea that we are talking about things which are changing. Now, we will do the proof, but to do the proof we will come in a stepwise fashion. So, I will keep the theorem up here and rub and start working on this part. So, we are going to do the proof in two steps. First, we will discuss a result by a little known French mathematician called Rolle, whose claim to fame seems to be this theorem called Rolle's theorem, which gives us an easy way of proving the Lagrange mean value theorem. But though if you know the Lagrange mean value theorem, the Rolle's theorem can also be proved. It is essentially some sort of a special case of that. So, let us first prove the Rolle's theorem and then apply the Rolle's theorem to prove the Lagrange mean value theorem. So, what are the ingredients of the Rolle's theorem? What does it say? What are the things that are there, and what does it say? So, as before, let us have a function f from AB to R. Here you will observe that in all the cases we are assuming the continuity at over the whole interval AB, closed interval. So, at the left and right end points, I am essentially talking about left continuity and right continuity and left continuity. So, but I do not bother about the derivatives at the end points. I am happy without that. So, let us have the following. Number 1 point, f is continuous on AB. 2, f is differentiable on AB. So, I am just giving the shortened continuous differentiable. And number 3 is an important assumption. It says that f of A must be equal to f of B. So, if these three conditions are satisfied, then there exists x in AB such that f dash of x is equal to 0. Now, how do I prove this result? Now, you will see whatever you have learnt in the classes previously will now come to your help. So, this pictorially this result looks like this. So, this is your A and this is your B. So, f of A, this is f of this is the f of A and this length is f of B, and f of A is equal to f of B. So, it says like if you start rising from here, you would again have to fall back to FB. So, there must be a point where you reach the maximum. So, you climb the hill and get down on the other side, or it could be like this. So, you descend to the valley and get up on the other side. So, you will have a minimum. So, at those points f dash x would be equal to 0, which you already know. Now, the proof depends on this result, which again is a very important one, which you already have studied. Since f is continuous, sorry, okay, differentiability would be always on the open interval, please, that is a, I would say, wrong writing, but I am mentioning it over and again, that, and I have also made a special lining that it has to be a special mark, that it has to be on the open interval. Since f is continuous on AB, so f is bounded above and below, that is what is the result. So, f is bounded, so it implies that f is bounded and the bounds are attained. So, there exists an x in AB for which fx is the maximum, or fy and fx is the maximum, there is some x dash for which fx dash value is the minimum, and the bounds are attained, Now, suppose first case that the maximum is achieved at say the point A. So, if x equal to A is the maximum point, okay, then B must also be the maximum point, right. If x equal to A is the maximum point, then B must be also the maximum point, because f A is equal to fB, right, and because the function is continuous, there must be a minimum value in between. So, it would implies that by 3 B is also the maximum point. But as you know, because of the fact that the bounds are attained, there must be a minimum value also of the function. There must be an x for at which the function attains the minimum value, but then that x cannot be lying at either A or B, it has to lie at some point in between. So, which implies there exists x element of AB such that x is the minimum point. and this implies that f dash x equal to 0. Of course, if there both the minimum and maximum lies in the interior in open interval AB, then anyway f dash x equal to 0. The same argument can be given if say x equal to a is the minimum point, then f x equal to b is also the minimum point because they are equal. So that is the crux idea, that this equality, this is the crux, and hence it does not matter, right. So basically if you write this result as f dash x into b minus a is equal to f b minus f a, then if I put f b is equal to f a, then what would happen? F dash x into b minus a is equal to 0, and if b is not equal to a, then f dash x must be equal to 0. So that is exactly the thing. So you can think of it as a special case of that result, but that is used actually to prove this fact. So you can argue for the other cases also, I am not arguing, and now I am going to prove to you the actual result, right. So now we are trying to prove the real Lagrange mean value theorem, and with that we will finish our discussion. And this proof is from Spivak, a book which I have been using. Of course, everything is not, I am not telling from Spivak, where things are so elementary you can just keep on telling, and these are very standard material. But okay, some proofs are taken from specific books and we should really mention them. And secondly, now how do I prove it? Well, what is happening here? There is that, okay, this is my AFA and this is my FB, some sort of a line. So this is AFA and BFB. Basically, given any function value, I would create a function where I would like to know how far, so this is the line. I essentially want to know for at any x, how far is this function from this line, right. Because even if you think about a travel, right, the best way to travel from point A to point B is to move at a fixed speed and go, but because of the car does not go at a fixed speed, you essentially have a curve like that, the curve that you saw in the case of the physical explanation. So here basically we are now trying to take for any x from fx, you are trying to know the distance of this line. So what is this line? So this line has a slope, this given line, if I call it L, so slope of L is equal to FB minus FA by B minus A, right, this is the slope. So this is your M. So what is the equation of this line? This equation is y equal to mx plus c, right. This is, or I can call this as g of x if you want. So what happens when x is equal to a, right, then y is equal to fa. So fa is equal to, you know already the slope, which is fb minus fa into b minus a into x plus c. So what is c? C is nothing but fa minus, so x is a, sorry, fb minus fa. So when x is equal to a, y is equal to fa naturally, and then you are putting it in this line because afa is lying on this line, and so this is my constant. So finally my function gx would look like fb minus fa by b minus a into x minus a plus fa. So basically I would like to know the difference between fx minus gx, that is the key idea. So I construct a function hx So now what is my So, this function is obviously because f is continuous in closed interval a b and differentiable in open interval a b, h also satisfies the same properties. Now, what is my h of a? H of a is equal to f of a minus g of a. So, what is g of a? If I put x is equal to a, this is 0, g of a is equal to f of a. So, in h, so f of a minus f of a is equal to 0. Now, what is h of b? H of b is, if I put, so it is f of b minus g of b. So, this is b, if I put x equal to b, b gets cancelled, b minus a gets cancelled, f a gets cancelled with f a, and this is nothing but, so just a moment, it becomes equal to fb. So, gb, fb minus gb, so okay, so fb minus, in this case if you put gb, so gb is nothing but fb, because if I put here b minus a cancels, f a cancels, so this is gb. So, gb is nothing but fb. So, you will have fb minus fb which is equal to 0. So, now h is a function which is having continuity over the closed interval, differentiability over the open interval, and h of a is equal to h of b equal to 0. So, which means there exists x such that h dash x is equal to 0. So, what is h dash x? H dash x is equal to f dash x minus g dash x. So, h dash x is equal to 0. So, 0 is equal to f dash x minus what is g dash x. If I take g dash x, it is nothing but, this is constant. So, it is nothing but fb minus x minus a, the derivative is 1, fb minus fa by b minus a. So, finally, we will get this result that fb minus fa by b minus a is equal to f dash x, and that is the proof of the Lagrange mean value theorem. So, with this proof we end our discussion today, and we will continue in the next class where we will talk about the applications of this particular result, and you will see a lot of things will come in. We will start talking about monotone and increasing functions and a huge amount of applications, because there you will see, because you will have knowledge about the derivative, you can draw conclusions about the function as simple applications of the mean value theorem, and by this simple result can give us huge amount of information about a function once you know something about its derivative. So, this is something very important, and these two lectures have to be, if necessary, go back to them and listen to them off and on, because these are very important chapters, very important lectures and very important results. Thank you very much.